Alright, in this video I'm going to talk about briefly on the remainder of alternating series. Okay, so there is a theorem that helps us to find out the sum, because so recently we have been working only on the convergence or divergence of the series. Okay, but we did not find out if the series converges, then how much is that number, where does it converge, or what is the sum. We haven't talked about that. We just talk about whether the series converges or diverges, meaning if the series has a finite sum or not. Okay, so in case of the alternating series, sometimes you can approximate what is that sum, where does it converge, kind of thing. Okay, and again I want to remind you that how do we check the convergence of a series is, so how do I find out the limit of the series, right? Where does it converge? Well, how do I find out the sum of the series? Is we usually find out the sequence of the partial sums, right? And if the sequence of the partial sum s sub n converges to a number, that number is basically the sum of that series, or that series converges to that number. Okay, a series converges to a number where the sequence of the partial sum converges. All right, so let me read that theorem. It says that if a convergent alternating series satisfies the condition an plus 1 is less or equals to an, then the absolute value of the remainder Rn involved in approximating this sum s by Sn is less than or equal to the first neglected term. What does that mean? That means Rn is the remainder, okay, s minus Sn, which is less or equals to an plus 1. What does it say is, do you remember that in section 9.2 we talk about the convergent of a series, right? To find out the convergent of a series, what did we do? We found s1 is a1, s2 is a1 plus a2, and then we did like that, Sn equals to a1 plus up to an. That's what we did, right? And then we find out the limit of limit n tends to infinity Sn. That's what we find. If it is s, then we say that the series converges to s. That's what we did, right? Now look at this. If the alternating series converges, then let us suppose that the alternating series converges to s. Then s will be a1 plus a2. That is the sum of the terms of the series, right? So a1, a2, a3, and so on, right? Now, so usually when we because we cannot find out all the terms of a series, right, because there are infinitely many terms, so what we do is we find out the first nth term, and then we find the limit of Sn, right? That's what we did in section 9.2. Now look at this. When you approximate the sum of the series by sum of the series n equals to 1 through infinity an by the partial sum, then we will be using only the Sn, the first n terms, right? And we find out the limit of that, and we denote by that by s, right? But when you do that, you are ignoring the terms after an, right? All the terms will be ignored, right? And that term we call remainder. Okay, that term meaning the total term minus Sn. The s is the sum of the total term minus Sn is the sum of the first term. That is called the remainder. Okay, that is called the remainder. And this theorem says that the remainder is always less than the first term. The whole remainder is always less or equals to the first neglected term. In case of the converging alternating series, the remainder is always less than or equal to the first neglected term, or the first term that we ignored. That's what it is saying. Okay, so basically it is saying that s minus Sn, the absolute value of that is less or equals to an plus 1, or you can write Rn is the remainder after nth term, right, is less or equals to an plus 1. Excuse me. That's what the theorem says. Okay, so let us apply this theorem to do some of the example. On example 1, what it says is says approximate the sum s. Okay, it says approximate the sum s of the series The series is given by n equals to 0 to infinity 5 over n factorial using the first 6 terms. That's what he's saying. Okay, so how does the first 6 terms look like here? Let's write down solution is, what is the S6? That is the sum of the first 6 terms. Will be, let's plug in 0. You get 5 plus, okay. Oh, by the way, there is negative 1 to the n. I forgot that. That is basically question number 31 from the book. Okay, so if you plug in 0, you will get 5 over 0 factorial, right? Because negative 1 to the 0 is just 1. Okay, and then the next term will be what? The next term is negative 1 to the n. Let's plug in n equals to 1. What do you get? You get 5 minus 5, right? And what is the next term? That's the second term. The third term will be plus 1 5 over 2 factorial is 2 minus 5 over 3 factorial is 6, and then plus 5 over 4 factorial is 24. Okay, and how many terms? 1 2 3 4 5 6. So 6 terms minus 5 over, what is that, 120. That's what we got. Okay, so what will be the 7th term? So the theorem says that s minus sn will be less than the 7th term. Okay, so we'll find out the 7th term. Because you see that since it starts from 0, 7th term can be obtained by taking n equals to 6, because it is starting from 0. Okay, this for n equals 0, n equals to 1, n equals to 2, n equals 3, n equals 4, n equals to 5. So if you use calculator to find out this, you will get 11 over 6. That is 1.9 something. That's what you will get if you use calculator. Okay, now what is a sub 7? A7 is, if you plug in 6, you will get 5 over 7 factorial is 720. If you use calculator, or if you divide it, you will get 1 over 144. But this theorem, by the alternating series remainder theorem, let me write down that. By alternating series remainder theorem, we get what? S minus S6 is less than A7. That's what the theorem says, right? Now, what is S? We don't know S. What is S6? Is 11 over 6 is less than A7 is 1 over 144. Okay, now how do I simplify this? Do you guys know this? If you have A is less than 5, this can be written as, let me write down slightly differently like this. If you have x minus 2 is less than 5, to get rid of this absolute value, we write like this. Negative 5 is less than x minus 2 is less than positive 5. That's how you expand this absolute value. Okay, negative 5, negative of that number on the left, and then that thing in without the absolute value is in the middle, and then that same thing on the right side, and then you add 2 on both sides to get rid of that. Add 2. So what do you get? Negative 3 is less than x is less than 5. That's what you do. Okay, so similarly, if you do that, what do you get here? You will get negative 1 over 144 is less than s minus 11 over 6 is less than 1 over 144. That's what you get. Okay, guys, now what do you do next is just add 11 over 6 on both sides. Plus 11 over 6 plus 11 over 6 plus 11 over 6. You can use calculator for that. If you do that, you will get 1.8264 is less than s is less than 1.8403. You can write less or equals to. Okay, no problem. Less or equals to there. So what do you get is the sum of the series. The sum of the series. This series, sum of that series is between 1.8264 through 1.8403. So you can basically approximate how much is the sum of that infinitely many terms here. Using the first 6 terms, we found that the sum of that series is 1.8264 and between 1.6 to 8264 and less than 1.8403. That's what we get. Okay, that is one of the application of this alternating series remainder theorem. All right, let us do another example. What it says is determine the number of terms, okay, determine the number of terms required to approximate the sum S of the series -1 to the n plus 1 over n to the 5 with an error. So the error must be less than 0.001. That's what the question is saying. Okay, now we use the exactly same theorem. What it says is by the alternating series remainder theorem, we know that Rn, the remainder is less than what? Remainder is less than a n plus 1, right? That's what we know, right? So what is the remainder? Remainder is that error, right? Because you see that when we approximate the S, the total sum of the series by partial sum of the sequence of the partial sum Sn, then we will be ignoring that. That will be the error term, right? So the error is given as 0.001. So what I'm going to do here is, what it says is, what is an plus 1? So here, what is an though? An is equals to what? 1 over n to the 5th, right? So an plus 1 is basically 1 over n plus 1 to the 5th. That's what we got, okay? So the error must be less than 0.001. That's what it says. So the error must be less than 0.001 means 1 over n plus 1 to the 5th must be less than 0.001. Okay, so the error must be less than 0.001, meaning that the an plus 1, which approximates the error, right, that must be less than 0.001. Okay guys, now how do I do that? Is if you just kind of cross multiplication thing, right? There is you can do this way. Let me write down like this. So 1 over n plus 1 to the 5th, right, is less than 1 over 1000, right? That's what it is. Now take the reciprocal. What do you get? When you take the reciprocal, then inequality will change, right? So what do you get there then? Then you get n plus 1 to the 5th is greater than 1000. Okay, that's what you get. Now what should be n then? If n equals to 1, what do you get? If n equals to 1, 1 plus 1 will be 2 to the 5th is greater than 1000. No, that is not true. If n is 2, what do you get? 2 plus 1 is 3 to the 5th. 3 to the 5th is 243. Is greater than 1000. No. If n equals to 3, you will get 3 plus 1 is 4 to the 5th is 1024, right? Which, so n equals to 4 works. N is equals to 4. N equals to 3, because when n equals to 3, then that makes 4, right? So n equals to, so we need 3 terms to approximate. We need the 3 terms required to approximate the S, so that the error is less than 0.001. Okay, so basically after you find out this inequality, okay, then you just try different values of n that works, that inequality, that satisfy that inequality. Okay guys, so this is how we use the remainder of the alternating series test. Okay guys, so the next thing we want to do is we want to define a new term called absolute convergence and the conditional convergence. All right, let us see that. So let us introduce a new concept of convergence we call absolute and conditional convergence. Okay, so sometimes some of the series, they may have positive and negative terms, but not alternatively. Okay, not like plus minus or minus plus like that. Some of the terms are positive and then positive and then negative and then positive and then negative. So it does not come in a certain pattern. Okay, it doesn't follow the patterns, alternating patterns. So in that case, if the series is alternating, we have the theorem to check the convergence or divergence of the alternating series, right? But if the series is not alternating but still has positive and negative signs in the terms, then the alternating series theorem cannot be applied. Okay, now in that case, So maybe if we can use kind of comparison type of thing, like for example, if you get the series without any the same term but without any negative sign, meaning that all the terms change the negative sign to positive sign. If you can say that that series converges, then the series with some of the negative sign must converge, because all the sign change to positive makes a bigger series, so the smaller series will converge, right? So that's the concept. So here some of the series may have positive and negative signs, okay, but not alternating series, because to be alternating series you need to have plus minus like alternatively, or minus plus alternatively, okay. To see the convergence of such series, usually we use we use the test convergence. We usually test convergence of absolute term series, okay, series of absolute terms. All right, so let us see a theorem. It says that if the series of the absolute term, you see that absolute value of an here, if the series of absolute term converge, then the series without absolute term also converge, because this will be the bigger series. If the bigger series converge, the smaller series definitely converge, okay. Let us see example. All right, let us see this example. So it's what it says is, does the series n equals to 1 through infinity negative 1 to the n over n to the cubed converge? Okay, so it says, does it converge? All right, so here let's suppose that s of n is equals to negative 1 to the n cubed. So I'm not saying that, you see that. So what I'm saying is I want to check the convergence of this series. So what I'm trying to do is trying to check the convergence of the absolute values, okay, which is definitely bigger than the given series. And then if the absolute value series convergent, then the regular series converge, right? So I'm taking that a n equals negative 1 to the n over n cubed. So absolute value will be 1 over n cubed. So since, does this converge n equals to 1 through infinity 1 over n cubed converge? This absolute value series converge by what? P series test, right? Converge because that n to the p is greater than 1. By P series test, then the regular series negative n equals to 1 through infinity negative 1 to the n over n cubed also converge. Okay, so basically we call this series converge absolutely. So this series converges absolutely, okay. So the series converges absolutely. We call this series converge absolutely because the series of the absolute term converge, okay. That's why we call this series converge absolutely. How about this one? So what is the series of the absolute term? Since summation n equals to 1 through infinity 1 over 3 to the n. This is the series of absolute term, right? Because if you take the absolute value, then you will get 1 over 3 to the n. Does this converge or not? What do you think? So this series converges by the geometric series test, right? Because you can write this as 1/3 to the n, right? And then the geometric series with common ratio 1/3, which is less than 1. Converge by geometric series with r less than 1, absolute value of r less than 1. So the series converges absolutely, right? So if the series converges absolutely, then the regular series converges, okay. The series converges. Absolute convergence implies convergence. So the series converges. So converge means so here it converges absolutely, meaning the absolute value series converges. If the absolute value of this series converges, then this series also converges, meaning that absolute convergence implies the convergence, okay. But some of the series, the regular series converge, but the absolute value series does not converge. That case is called conditional convergence, okay. Look at this. If the series n equals to 1 through infinity converges, but the absolute value series diverges, it is called conditional convergence, okay. If the absolute value series diverges but the regular series converge, then it is called conditional convergence, okay guys. So let us do this example here. So what do you think? Does this series converge absolutely or conditionally? We want to check that. Okay. So the series here, you see that it is an alternating series, right? This is an alternating series. Does this alternating series converge? It converges. You look at this. So the given alternating series converge by alternating series test. What are the alternating series tests? If you take an equals to 1 over n plus 3, so this is basically what is happening on an is all of these are positive, right? And the limit n tends to infinity, an is 0. Also an is decreasing. Okay, so it converges absolutely. Sorry, it converges. So this regular series converges. Now I want to check, does it converge absolutely or not? Or does it, if it doesn't converge absolutely, this series converges, but if its absolute value series also converges, then it converges absolutely. If the absolute value series does not converge, just this series converges, then it is called the conditional convergence. But let us see. The series of the absolute term n equals to 1 through infinity, if the absolute value is 1 over n plus 3, okay, so does this converge? Does not converge. Oh, n equals to 2, I think. What is that question? Was the question number, let us see, that was question number n equals to 1, question number 44 from the book. Does not converge. How? Let us check that. So here this, so we can use the integral test for that, because this series does not converge, because if you do 1 through infinity 1 over n plus 3 x plus 3, the integral test, okay, 1 over x plus 3 dx, that implies limit r tends to infinity, right? And then you do natural log of x plus 3, but it is going from r through 1 through r, right? If you do that, you will get infinity here. So this integral does not converge, meaning the series does not converge. Okay, so the given series converges, but the absolute value series does not converge. Did you see that? The given series converges by this given series converges by the alternating series test, right? But the series of the absolute values does not converge by the integral test. So the series converges. So the series converges, the given series, the series converges n equals to 1 through infinity negative 1 to the n plus 1 over n plus 3, converges conditionally. This converges conditionally because the regular series, the given series converges, but the absolute value series does not converge. Okay, so it converges conditionally. All right, next, test the convergence of this series. So we want to see if it converges conditionally or absolutely. Okay, what do you think? So this can be written as n equals to 1 through infinity negative 1 to the n plus 1 over n to the 3 half, right? Because n to the 1 and n to the 1 half becomes n to the 3 half. So do you think that this series converges absolutely or not? Okay, so since summation of n equals to 1 through infinity 1 over the absolute value of that negative 1 to the n plus 1 is 1 over n to the 3 half. Do you think it converges? Converges because the series of the absolute term converges by what? By p series test, right? P series test. Why? Because it is n to the p, right? And p is greater than 1. So this series converges. So the given series converges absolutely. Okay, the given series converge absolutely means this series also converges. Okay, because if the series of the absolute term converges, the given series also converges, because the bigger series converge means smaller series converge by comparison test. Okay, so that series converges absolutely. Let us do another example. We have test the convergence of summation of negative 1 to the n over n natural log of n. Okay, that's what we want to test next. Okay, so does this series converge, or does the absolute value of the series converge? Let us see. So let us see the absolute value of the series. Okay, so here summation n equals to 2 through infinity 1 over n natural log of n. Do you think this series converges? We can use the integral test, right? As 2 through infinity 1 over n natural x. Let's do x. 1 over x natural log of x dx equals to what? You will see, basically you will see, so if you use the u substitution for natural log of x, 1 over x dx will be du, right? You will get, and when you change the limit, you will get natural log of 2 through infinity, okay, and then 1 over u du. If you do that, you will get limit r tends to, I think we have done this type of problem in the integral test. R tends to infinity, natural log of u, okay, and then natural log of 2 through infinity. If you do that, you will get infinity. So the series of absolute term diverge. The series of absolute term diverge. It doesn't mean that the regular series diverge. Now I want to test if the series converge, if the regular series converge. Okay, so no absolute convergence, meaning no absolute convergence, no absolute convergence. Now I want to test if this series converges by the alternating series test. Okay, also let me use different color. An is equals to 1 over n natural log of n. This is positive for n greater than 2. Also this series is limit n tends to infinity, an is 0 for n is greater than or equals to 2, right? That's what we got. Okay, so also this series is less than, because if you find out the derivative, you will get negative, so it is decreasing. An plus 1 is lesser equals to an, okay, for n is greater equals to 2. That means what? So this means the series converges by alternating series test. By alternating series test, the given series converges. Summation n equals to 2 through infinity negative 1 to the n over n natural log of n converges. That one converges. You see that the regular series converges, but the absolute value series does not converge, meaning it converges conditionally. So the given series converges conditionally. Okay, so this much for this section 9.5. okay, so in the next video we will see more tests there. So there are so many tests to test the convergence or divergence of a series. All right, guys.